So the remainder of chapter 5, that we'll just talk about these in general. 519 is armature reaction, and we'll look at some of the figures here and just talk about this. Not too much emphasis on it. Up to this point, we've assumed the only magnetic force in a DC motor is that due to the field. But once there is current that starts to flow in the conductors, once a load's connected to it, any current carrying conductor has its own electromagnetic forces created, so it creates its own field. Okay, and so what happens is there's an interaction of two fields, and so we can see that in 520. So this would be the flux in a motor running at no load, right? It's just strictly coming from the magnetic poles that we have. Here it's just showing the one north pole, and then we see the flux, you know, in the distribution pattern from that. All right, so that's pretty straightforward there. Then we go to the next slide, and this shows what happens once we connect this motor to a load. Current starts to flow in these conductors, and when current starts to flow in a conductor, there's a magnetic field associated with that current flowing through the conductor, and so this represents what we'll call the field 2. And then so finally, the third slide here shows what happens with the interaction of those two fields. Okay, and so we call that this flux 3. So there's a distortion to the field as a result of the interaction of the two fields when connected to a load. And you know, he talks about that in 519, 520, and then the solution to that, and to improve or counter this effect, we add what are called commutating poles. Okay, and commutating poles can actually be seen in this photograph right here. This would be a commutating pole, and this would be a commutating pole here. And the design of this is such to counter the effects of the two flux fields interacting, and improve what we call the armature reaction for that. 522 talks about another thing called a compensating winding, and a compensating winding does the same thing in a sense. It's a stabilizing effect that it has on the operation of the motor. And let's see, this is a, let's just say this is a 6-pole motor, and so we should see compensating windings distributed throughout here. Let's see, 6-pole motor compensating in the slots of the main poles. And then, so, you know, we can see the effects of what we call these compensating windings. So we just want to know, you know, basically what that is. 523 talks about basics of speed control, but we'll sort of hold off on that until we get into our 3-phase induction AC motors. And then the last thing here is permanent magnet motors. Permanent magnet motors are very simple, because you don't have to concern yourself with creating a field. And so, you know, the field is supplied by a permanent magnet. Now, this motor that's shown here, it says it's a 1.5 horsepower, 90 volt, 2900 RPM, 14.5 amp permanent magnet motor. We're limited in the use of those. They tend to be smaller size motors, and they also tend to be expensive because what happens is that the magnets that are used in these motors are very expensive. But again, the neat thing about this is that they don't require any type of field connection. And we actually have one of these in our lab, and I'll show it to you later. And it's, I think, like a 2 horsepower motor, but it's very expensive. It's $1,500, $2,000 motor. But it's a permanent magnet motor. Okay, so that wraps up chapter 5, and we'll move from there to other exciting places, and I'll stop talking there, and we'll wrap this up.